Okay, so we've been trying to define what a vector is on a manifold. And what we've done is we've identified a vector with a directional derivative. And we've said a vector is something that operates on all the functions that go from the manifold to the reals. Okay, so it's not on a specific function, it's just something that operates on all the functions, just like the derivative operator operates on every function. Like for every function, you can define a gradient, and then you can dot that gradient in with a vector, and that will give you a directional derivative. So it's exactly analogous over here for the manifold. The only difference being, of course, is that everything is well defined for a manifold, because you can always have a map, a function that takes the manifold to a real value, and then do the operations on that. And then we went on and we said, fine, if we have this definition, we can actually prove that this is a vector space, okay? And we can prove the dimensionality of that vector space is the same as the manifold's dimensionality. And the way we did that was to basically make up a whole bunch of basis functions for the vector space. And I'll give you a clearer picture of what that is. But what we basically did is we defined this quantity x of mu, where we used the fact that we had a chart from the point P to the reals, okay? And then the function that took that point P to the real line from the reals was this f circle phi inverse, okay? So this function actually arrived at the same real value, and then what we did is let us examine how that value changes if we take partial derivatives with respect to the Cartesian coordinates on Rn. Okay, so we used the fact that we had a chart from the manifold to Rn to get the idea of partial derivatives with respect to the Cartesian coordinates on that Rn, and then we used those to make the basis for our directional derivative on the manifold. So it's a very clever construction, but it's rigorously correct. And then we said this allows us, because the Cartesian coordinates on Rn are independent, these derivatives will all be different, and so we can have n linearly independent vectors that we've constructed in this way. And what we now need to show is that these vectors actually span V. In other words, we've shown that there are n basis vectors, so the dimensionality has to be at least n, but we must show that any vector V of P can be written in terms of these basis vectors. And to do that, what we're going to do is we're going to use a result from calculus, which is very closely related to a Fourier expansion. Okay, so in calculus in Rn, so this is just ordinary Rn, we have, suppose if we have a function for Rn to R, okay, and it's C infinity, and then suppose we have a point A in Rn, okay, so any specific point in A, then there exists a series of C infinity functions h of mu, such that for all x in Rn, you have the following identity, okay? So here we have f of x equals f evaluated at A plus the sum from mu equals 1 to n of x minus A mu h of mu x. Okay, so look at this thing carefully. It looks a bit like a Fourier series, but it's not. It's resummed all the higher order terms into h. Okay, so this thing is more general than a Fourier series, because a Fourier series, when you work out the Fourier series, you have to work out the radius of convergence. You have to prove that in the Fourier series, the higher order terms actually will converge to the right answer. Okay, this thing, you don't need that. It's a much stronger statement. All it says is that any function can be written as the function evaluated at the point plus x minus mu, where you've actually taken out the deviation of the function in every single direction from the point multiplied by another function h of mu, which is continuous. Okay, so what you can do, one way of constructing h of mu, if you have a Fourier series that converges, is to work out that Fourier series, subtract off f of a, and then take out that common factor x of mu minus x minus a of mu, and then put everything else into h. Okay, so this is more general than a Fourier series. It is valid for anything in Rn provided it's C infinity. Okay, and it doesn't need the fact that you need a radiance of convergence for your Fourier expansion. So this thing is generally true. And so what you also have is that at x equals to a, h of mu is df dx of mu. Okay, so there you can once again see the reminiscence of your Fourier series, but it's not. It's more general than that. Okay, so you can literally rewrite f as the function evaluated at a plus this deviation from a multiplied by smooth functions. And that we're now going to use to actually prove that any vector on the manifold can be expressed in terms of those basis vectors. And we're going to use what we know for the definition of a vector and what we know for the definition of a manifold to do so. Okay, so here is just the picture again to remind you. I will keep on coming back because I like these pictures. They tell me, they keep track of what I'm thinking. So here we have our manifold. Here we have the open set of which every point is a part. Here we have the map phi that takes it to the reals. Here we have the image of P, that particular point. Okay, here we have the image of the whole U, the little u, so that's that whole set. And here we have that function from the reals from the Rn to R that we use to define the basis. And this function effectively takes this point P that's been imaged over here onto the value of what it would have been if it had gone straight to the reals. So if you look at this, if you apply f circle phi minus 1 to phi of P, all you actually get is f of P. Okay. So here we have the function that we worked out, used to get the basis. And now let's basically prove that the basis spans the vector space. So what we're going to do is we're going to apply this above result to the very special function that we've constructed from Rn to f. In other words, f circle phi minus 1. We want to apply this above. We want to set f equals to that and apply that theorem to it and see what we get. Okay, so in this particular case, the particular point where we want to evaluate the theorem is at A, right? And that A is phi, is the image of P. Okay, so we want to do it in a way that we can eventually relate it back to the point we started with at the manifold. So A is phi of P. And then what we're going to say is for any other point in U, in other words, so for any other point, say Q is over there, some distance from P. Okay, we're then going to say X is simply phi of Q. Okay, so for any Q in U, we have that basically F evaluated in Q, in other words, this F that goes back down there is equals to F evaluated at P plus the equivalent of this thing. Okay, and the equivalent of this thing I have written like this. Okay, so that's basically the coordinates of the image of Q, so that's x of mu, minus the coordinates of the image of P, that's A of mu, okay? Because remember, these coordinates will simply give you the value of those coordinates on the real line. So that's what those functions do. Okay, times h of mu evaluated at x, and x is phi of q. So this one, your problem's here. Not yet.
Are we going to do like an example with this? Or?
I am going to, well, we can see how far, we can see what I've got. I'm going to most probably prove the theorem and then give more practical examples. Okay, but do try and track what the function, which functions are going where and how it's defined. So actually go through it carefully and try and sort it out. Yeah.
So therefore f of q, is it f of q or f of phi of q?
No, so f of q is the value that the function does when it maps it to the real line. So you have a q here, f of q is mapping it to over there. So f of q is a real number, okay? And we're evaluating f of q by knowing what the value of p is and then using this thing for the deviation from that. So we have p over there, we have q over there. We have the chart of p over here, and then we have the chart of q over there. Okay? The chart of p has coordinates that, right? The chart of p is a, which is phi of q. So x mu circle a are all the coordinates of a. Okay, in other words, it's the coordinates of this point. That's what the second thing means. This first one means the coordinates of the image of q. So it's all the coordinates of this point where it's mapped on. Okay, and that is effectively my x. Right? And then what we have is this h, which we guarantee to have this expansion function evaluated at x, which is basically the point, the image of q over there.
Is this what we're eventually going to use to determine distance between points?
It's going to get simpler. We're going to use this to define what a vector is. And we're going to use this to prove that you can actually find the vector space in there. Then you're going to have specific examples where you actually construct this basis. In fact, you've constructed this basis for the two surfaces in your problem set already. Okay, but I'll get back to that.
So big F of phi q is just small f of q?
No. Big F of phi q.
Yes, because x is phi q.
Isn't it
X is phi q. So big F, big F of phi q is just phi q. It's just a little f of q, yes.
Okay.
And you can see that because big F of phi q is just f circle phi minus 1 times phi of q.
Yes.
So phi minus 1 circle phi is 1. So it's just f of q.
Yeah.
Yeah.
Is the big F, yesterday we said f prime, is that the same function?
F,
Because
it's
F-
this combination, yeah.
Okay, so f prime and big F
Is what, yeah.
is the
Yeah.
same,
Okay, so now let's go on and we're going to say let V be a function of the vector space at P. Okay, so V is being defined at the specific point over here, that's P. Okay, and what we want to show is that V is a linear combination of x1 to xn. And so what we're going to do is we have an expression for this function. And never forget what a vector is. It's always something that you apply to a function. And this function is as general as you can get. So let's apply this V to F. Okay. So if we apply V to F, what we get is, remember F of P is a constant, is a real number. Okay, so V applied to a constant, which we proved in the previous slide, is 0. Okay, and we proved it rigorously in the previous slide. It's not totally an obvious thing. Okay, then what we're going to do is we're going to apply Leibniz's property, and we're going to apply V to this whole bracket.
Sorry.
Yes.
Aren't all V's then going to be 0?
No.
Because we can project every point to a real number. So, and then we take the V of a constant.
No, you can't do that. Right, look, this function is written as a constant plus another term. Okay, this is the most general function you have. And so when we apply V to this function, yes, the constant term is going to fall away like it does whenever we differentiate. But you've still got to apply it to this nasty little beast, which is where all the details lie. Okay, so let's do that. So we're going to use Leibniz's property and linearity and apply it over here. So linearity means we can treat each sum independently, in other words, each component, because this thing goes from 1 to n. And we can, Leibniz means we first differentiate here, multiply with that, and then differentiate this thing, multiply with the other stuff. Okay, so V of f is equals to V of p, which we've just argued is 0, plus, we're first going to apply V over here, V times this h mu circle phi times by this thing. But this thing then we have to evaluate at q equals to p. Right? Remember that definition you asked me about the vector, Leibniz's rule, where you said, must I have the p in there? And the answer is yes, because you had to get a real number. So here we're evaluating these coordinate differences at q equals to p.
And then it's just 0.
Yes, exactly, well done. Okay, so then this thing falls away, and then we have the second term where we have this h of mu circle phi evaluated at p, but now v applied to this thing. Okay, and so what we have then is the coordinates of this thing is a constant, right? Because p is known. P has real coordinates, and so this function evaluated at a, all the coordinates evaluated at a are just constants, so that falls away, and you are left with v applied to x of mu circle phi.
So for us to determine whether these functions like holds for the condition, we have to always determine the linearity and Leibniz.
So you are using the definitions. Remember, we defined the vector field to be something that maps all the real functions to the real function, all the manifolds on the function to the real line. And then we said it's that, it acts on that, and it has two properties. The one is Leibniz and the one is linear. So you can, whenever you prove theorems, you can only use those two properties with your vector field. Okay, for now, until we've derived others. But every single property of our vector field comes from those two properties. Okay, so here we now have, it simplifies to this. So we have these h mu functions applied to phi at p, okay, multiplied by the vector field applied to the coordinates of the image of p. Okay, the coordinates of the map of phi to Rn. Okay.
Is the v of x mu composed of phi, isn't that going to be a constant then?
No, it's not, because these things are functions. Okay, so they're not constant. If you evaluate those things at a specific point, it's a constant, but we haven't done that. Okay, because we've kept phi to be the function effectively of any point. Yeah, it's not specific. So it's very important to keep track of what is actually a number, what is a function, and what is a vector. Okay. And now what I'm going to say, this h of mu circle phi of p is just that basis we described earlier on. Okay, so remember, and to see that this h of mu circle phi of p is h of mu evaluated at A, okay, and A is phi of p, and this h of mu evaluated at A is simply the derivative of f, big F, evaluated at x at A equals to A, and that big F is F circle phi minus 1. Okay, so these guys that we have over here is simply x mu of F. So that is the basis of basically what we have shown is that any vector can be written as a sum of these guys over the dimensionality, in other words, 1 to the dimensionality, times the vector field applied to this beast. Okay. But the vector field applied to this beast is simply the vector field applied to the results of the coordinates. And so in some sense you view this beast as the components of the vector field on that basis. Okay, and so here we've basically gone and expressed this vector field of F equals to the sum of x mu F times V of mu. Okay, so complicated root, but it strictly defines what the vector field is going via the chart back to F. And it proves that if you have worked out these functions, you actually have a basis for your vector field, but only at that, it's only currently being defined at a specific point. Okay, so this is important. We can always write the vector field as an expression like this. One thing, note these indexes, and where we put the indexes are important. The components of the vector field are always up, okay? The basis of the vector field is always down. Do not switch the two, okay? Because then you are actually meaning a completely different thing. Okay, so we now have proved that a vector field has a dimensionality n that we've defined using Leibniz's rule of linearity on the map of all functions from the manifold to the reals. We've proven that we can get if we have a chart, we can get a basis for the vector field, okay, simply by taking the derivatives of those charts with respect to the Cartesian coordinates over here. And now the next step is basically the coefficients V of mu are simply the values of V applied to these functions. In other words, applied to the coordinates of the image of phi.
So those will be constants?
They will be values, right? Look, your V, always check, your V maps from here to reals. Okay, so at a particular point, these things will be real values, right? Okay, but these entities will not. These entities are actually directional or derivatives of a function. Okay, so you've shifted the fact that you have a vector field onto values over here at a particular point multiplied by ddx, ddy, ddz over here. And so this basis you've made is dependent on this chart. Okay, so now let's say we express, and there's a mistake, let's express an arbitrary vector field, vector v, as the sum of the nx mu's. Okay, so there we have the vector, and this part is now very intuitive and easy to work with. The theorem is heavy. It's very useful to sort out exactly the steps that you go through to get it to work. And it's not easy, I can tell you that now. But once you get it, and once you've separated out what the entities are, because that's the crux, realizing what the vector acts on, realizing what the functions act on, and keeping those straight. But once you have that any vector applied to F can be written as a sum of its components on this basis. Okay? And the basis, therefore, it's because it has the dimensional n, there are n coordinates that we use to construct these. you can say that these guys form a basis of the vector field. So this is just formal things. And this particular basis we're actually going to call a coordinate basis. And the reason we call it the coordinate basis is because it's literally constructed by taking derivatives in the one direction as opposed to the other direction on the actual chart that we have. There are other bases that I actually use quite a lot, but I will actually not do it now because it will confuse the issue. Okay. And so what we do to make it even more obvious that we're working with a derivative is we often write these x of mu's as ddx of mu, like that, with the implicit idea that there's a dot in here in the sense that you've got to apply it to a function. So those of you that did partial differential equations with me, I often did proofs where I just did that and I left out the function. And this is the reason why, because it has a very definite meaning. Okay. And if you think of this thing as having the intuitive meaning that you use for functions, you'd be right. In other words, writing this coordinate basis like here, like so, actually makes you make fewer mistakes, because you then know, it makes it very clear that the basis of the vector is a whole bunch of derivatives. Okay. Right, so there's our very useful picture again. And here is where it becomes interesting, right? So here we have our open set U. For that open set, we have a chart defined this way, okay? But we could easily have taken a different chart, okay? And this is simply to illustrate how this basis depends on the chart we've got. We could have had we could have taken the same U, and we could have said, okay, let us transform Rn to something else, and then we have a new chart that goes to Rn in a different way. And in fact, that you'll do in one of the exercises on the sphere, is you'll have a completely different chart from those hemisphere maps, and then the same result must still hold. Okay, so you have one chart, and this is where tensors start becoming powerful. You have one chart that does this particular thing. We haven't given you the specifics of the chart, we've just derived the result. So if you have another chart, phi prime, that also goes to Rn, that covers the same set, everything else remains the same, but you're actually going to get a different coordinate basis. Okay, because once again, it was defined as ddx in a specific direction. So if you have a different chart, you have a different coordinate basis. But the main thing now is you can relate the expansion on the one coordinate basis in terms of the other one. And this becomes crucial when we actually work with coordinate systems. So what you can do is you can express this coordinate basis in terms of the new coordinate basis. And because this coordinate basis is simply the normal derivatives in the various directions of your Cartesian basis, it's very easy to actually get. So you basically do it by the chain rule. So you have x of mu is simply ddx of mu, okay? But you know that this guy actually depends on mu prime. So when you take, you have the new coordinate basis is ddx of mu prime. Okay, so you literally express this thing as ddx of mu prime times dx d mu prime dx d nu. So it literally is the Jacobian that you're putting up here. Okay, so there's a transformation between the one coordinate basis, which is ddx of mu, and this other coordinate basis, which is just ddx of nu prime, that's over there. But to get the two to relate to each other, you simply express ddx of mu as the derivative in terms of every new coordinate basis times by dx d nu dx, dx d nu prime dx d mu, evaluated at your particular point. Okay, and this, as you'll see, is it is the Jacobian that we had. So our coordinate bases then transform by using the coordinate transformations between the two charts. Okay, so here x mu prime is the ith component of this map, which is basically you take the chart to the new coordinate basis, apply to the inverse of the chart to the old one. Okay, and now the components of the vector on the new coordinate basis, okay, are related to the components of the vector on the old coordinate basis. So here we have, you can always write the vectors on the new coordinate basis simply in terms of the vectors on the old coordinate basis multiplied by this transformation law. Okay, so you're literally using, you can view your vector v of f as an entity. You can either express it as the sum of x of mu of f, or you can go and you express it as this sum x of mu multiplied by our transformed version x nu of f, where you substitute that thing in, and then you group everything in front of the new basis and you call that your new vector. So not only do your bases transform, but your components actually transform as well with the same Jacobian coming in. Okay, and this transformation law is crucial. This is one of the ones you very often forget, the fact that you drop these guys and we used to keep just the components because we now know what it is. Okay, questions here. Go through it carefully. It's not something you're going to look at the first time and know how to do. It's going to take work. Right, so we now have vectors. We have the idea that we can express any vector, okay, on a basis. We also know that we have different charts. We can transform the vector on one basis to a vector on the other basis, okay? And so when somebody says you do a coordinate transformation, then you must immediately think you're going to start transforming the components like this. Okay? If you stick with one chart, then you just use the basis you've got. Okay? So now what we want to do is, so far everything we've done has been at a specific point. The whole argument for establishing the vector was at a specific point. We used the expansion of the function around that point to actually get the basis, but the vector itself was still always evaluated at the point. Now what we want to do is start finding a way of connecting vectors at a specific point to another point on a curved manifold. And so before we do that, we have to find a way of traveling, okay? And to do that, we want to define what a curve is. In other words, how we move in this manifold. And so what we're going to do is we're again going to start with our idea of a manifold, right? The open set with a chart. And we're going to define what a smooth curve is on the manifold. So our smooth curve is a C infinity map of R or an interval onto M. So remember when we defined the vectors, we said we want to operate on all the functions that map from the manifold to the reals. Okay. Now we want to define a curve that maps from the reals to the manifold. So the way we do that is we simply have our function R1, that's the real line, and we define our curve to be mapping from the real line to a point in your manifold. Okay. So, for example, if you think of the curves that we made on the developable surfaces, those were mapping from the reals, which was our parameter, onto R3. Okay. And here we're doing the same thing, simply taking an interval and saying there's a rule that takes everything single number from this interval and associates it with a point in our manifold. Okay. So what we can do once we've done that is we can say for each point P in M that lies on this curve, okay, we can associate a tangent vector. So we know for each point P, there are a general vector can be expanded on the basis which has dimensionality n. Okay. Now we want to say of that general vector, we want to associate only one vector that is actually tangent to this particular curve. And the way we do that is we once again want to incorporate our machinery for a vector. So remember, we defined a vector as a thing that operates on the set of all functions from P and to the reals. And we also, in order to define our basis, we had to go via this chart and this special function. So here's all the machinery we had for the vector. So for any f in any function in the field of all possible functions, we have that our tangent vector of f is equals to the derivative of f circle gamma, okay, and that is something that maps from R to R. Okay, so you see once again, I'm using the fact that I pull my manifold down to something I know on the real plane, and then I use that to define what my tangent vector is. Okay, so let's have a look at this a little bit more carefully, okay? So f is any function, okay? If you construct this f circle gamma, what you're doing is you apply gamma to the real line, so you're taking it to the manifold, okay? Then you apply f over here to your manifold, and then you take it to the real line. So the moment you've applied f, you can find a vector field of that f. Okay, so you can apply v to f and then take it to the real line, and we're going to say the specific vector is equals to the specific vector that points in the tangent direction is equals to the derivative of this combination. Okay, so effectively doing this thing, we've given a function from the real line to the real line, okay, and we then use the derivative of that function to give you the value of the vector field applied to f in general. Clever, yeah?
Can we draw it as two different real lines? Like we have a function for the gamma function is on one real line, so it's both R1, but because the point f of p can fall inside gamma, the region of gamma.
Yeah, you could do it.
So
Yeah,
I can draw just on two separate.
you can draw it as an axis if you wanted.
Okay.
In other words, real line in the one and real line into the other.
Okay.
Yeah, it's you can view it as two different real lines. Okay, because yeah, f of p can be anywhere. Okay. In fact, if your function, this isn't any function, if this function is a constant function, you haven't gone anywhere. Okay. So yeah, you can totally do that.
So f of p cannot be inside R, or it can.
Yeah, okay.
Okay.
Okay, so the tangent to my, the tangent vector associated with the curve is a vector, so it's applied to the function of f, and its value is simply the derivative of this combined function ddt. Oh, sorry, the derivative of this combined function. So intuitively, this thing actually, if you were to imagine the manifold was just Rn, then this thing would work exactly. In fact, that's not a bad exercise. If this thing is becoming vague, imagine the manifold is just Rn and get yourself an example that works. Okay.
Can we say, for instance, we have a ball and we have a string and we put it there, and then we take the string and put it on a ruler? So you put the string somewhere on. If we say this is a ball, we take a string and put it just somewhere like this, and then take the string and put it on a ruler.
Okay, that's a good analogy. So suppose you had your string on a ruler, okay, that would be your Rn.
Yes.
Okay. Then you take that string and you put it on the ball. And that's the map gamma that goes up there.
Okay.
Okay. Then you look on that point on the ball. Okay. On a particular point, you have a vector field that is spanned by, because you have a ball, it's 2 dimensions, that's spanned by 2 vectors. Okay.
Yeah.
Then what you do is you say you want to choose the vector so that the string you want to choose the vector in which the direction of the string is changing.
Okay.
So of those 2 vectors on your
So
ball,
like a principal direction.
it's not a principal direction because your string need not necessarily line up with the geometry of the ball.
Okay.
But in the example of the ball, it is a principal direction. Okay, because it curves the same way in every way. But suppose you had a peanut, right? You would not necessarily, so the peanut has a strict principal direction this way and that way. So if you put your string skew across, you would not be lining up with your principal direction. Okay, so you've taken the string, you've taken gamma, you've put it on the ball. Okay, at a particular point on the string, you've got a vector field that has 2 basis vectors. Okay, and you want the linear combination of those basis vectors that points in the direction that changes the same way as you change along the string. Okay, in other words, you basically want to get and that's why you connect the specific vector, tangent vector to the string with a value of this thing changing on the string itself. So you literally want your vector to point along the string as the string is changing on the ball. And that's what this construction ensures. So it basically, this T of F picks the vector which points along the direction where the string is changing. So if you put your string on the ball, your vector is basically, in some sense, in the tangent space, going to point along the direction where the string's going. So it is your very intuitive, direct idea of what a tangent does that you have structured correctly using this sort of functional thing. Okay, so now you have a coordinate basis vectors x of mu, and you have n of them. You have a chart phi, which helps you embed the Rn properties into your manifold. And given that, the tangent to the curve on M can basically be obtained by keeping all coordinates except mu of constant. Yeah.
Sorry, this is not particular to what we just did. Is the function gamma invertible? So can you go from the ruler to the string on the ball and back to the ruler? Is it an invertible function or not?
Yes, because every single point you identify with, it's basically a function. Like it's you can think of it exactly as what the curve we did in 3 space, right? For every single point on your ruler, you have a point on the curve. Okay, and they are ordered in the sense that as the ruler points increase, or points on the curve increase. So if I tell you I want the point at parameter x equals to 2, you know exactly what point I refer to. If I tell you I'm on the point on the curve, then you can take those coordinates of the curve and try and get out the parameter, because you know the relationship between the parameter and the coordinates. So yeah. Okay, so right, let's get back here. Okay, so we have a coordinate basis vector x of mu, and we're given a chart that maps the manifold to Rn. Okay. If we keep all the coordinates except x of mu constant, okay, we're basically taking the derivative of x of mu. We're basically taking the derivative of the basis vector is basically taking the derivative along one of these coordinate directions. Okay, so if we have this chart, okay, chart phi, the curve gamma on M will also map out a curve in Rn. Okay, so what we do is we have this curve over here, and if we use the chart, we can basically map this, every point on this curve onto a curve over here. Okay, and what we can then do is say our tangent vector f, to get its components, is simply the derivative of that combination, but we can get to that combination going that way round. And so what we can say, it's simply the derivative of f circle phi minus 1, okay, times d dx mu dt. So what this then gives us is that the components of my tangent vector are simply the way the coordinates are changing in Rn with respect to time, expressed on the basis vector that we've already defined. Okay.
So if I go back to my example of the ball, we can say like the charts can be, like we said, the semicircles, the 6 semicircles.
Yeah.
So, and then there will be a part of the string on each of the semicircles if it is if it falls on that part of the semicircle, and that can also map back to the real number line.
No, the charts aren't the semicircles. The charts can be, say, for example, your coordinates on your sphere.
Okay.
Okay, so your coordinates on your sphere can be like phi and theta. Okay, and then
So I want to say the projections of the semispheres.
yeah, you could do that. Would be one example. Yeah. Okay, and then if you wanted to work out your tangent vector, is you would actually then get a circle, or you would get the projection of the line over here onto those coordinates, and then you would simply behave as the way we worked with lines up until now, where you work out the dot of the line. Okay, so it would be like x dot times d dx. That would become your tangent vector components. Okay, you have to go. Yeah, I think we'll stop.